we will look at now the spatial consequence of the intensity dependent refractive index. Not only do laser beams have when their pulses have a Gaussian profile in their temporal envelope. Recall once again we discussed much earlier in this course that a propagating Gaussian beam, it is Gaussian because the beam which propagates, this is the propagation direction z, but then along the coordinate that is perpendicular to it, let us say this is an x, or we have used the symbol y here. So, this coordinate would have made it x y. Okay, then it can't be this way. The system is right handed, so let me not sketch that. This way it should, the x should go this way. But let me take that off for the sake of simplicity and point only to the y coordinate. So, now this is the profile of the beam, the Gaussian profile, which is given aptly by this expression E is E naught exponent of minus y square by y naught square, where y naught is a constant proportional to the width of this Gaussian, a measure of the width of this Gaussian, right. So, now as a consequence, since n is equal to n naught plus n to I, intensity also has the same profile, I is equal to I naught exponent of minus 2 y square by y naught square. The spatial Gaussian profile is imprinted on the intensity profile and hence also on the refractive index profile. Now, n, which is now a function of x, y, z, we can say like it was earlier a function of t, is n naught, this is independent of any spatial coordinate, times n2 of x, y, z. This now becomes n naught plus a delta n, which is a function of, in this case, let us say just y in this 2D scenario, where I am considering, actually it is a 1D scenario you can say, in which the intensity is varying only along the y direction. There could well have, there is a coordinate transverse to this, and the whole Gaussian beam, okay, has a particular intensity profile. It could be a surface of revolution of where the Gaussian revolves around, can be rotated along this axis, which is also the propagation axis, to produce the intensity contour of the beam. We have looked at all this earlier, but the point being that we now have a scenario where n naught remains independent of refractive index, delta n is imprinted on this as a consequence of propagating through the medium. Now, this scenario is no different from what happens when we have a lens. So, consider a lens, a biconvex lens, a positive lens, and a beam propagates through this. We saw this earlier. So, we have wave fronts, let us say planar wave fronts are incident on this beam. Now, if the refractive index of the medium of the glass inside is typically, let us say n0 is 1.5, then we can visually do some visual math and say that the center of this beam passes through a thicker amount of glass. So, after the passage of a time t, this face front has moved to this point. As I go away from the center, because the thickness of the glass decreases as we go vertically up or vertically down through the lens, the wave front essentially distorts, because the phase points farther away from the center would have propagated to a greater distance z because they experience lesser glass. As a consequence of this, going by Huygens principle, these wavefronts will now converge and this explains the focusing of a typical lens. Now, in the case of a medium with a certain nonlinearity, let us take a medium with an interface which is essentially sort of rectilinear, it's rectangular. All right. A Gaussian beam, a beam with a Gaussian intensity profile propagates through it as shown here. This is the intensity profile of the beam propagating through such a medium. Now, since the delta n, that is since delta n of y now also has exponent of minus y square by y naught squared form, this medium, we must define the y coordinate of this problem. This is the y, this is the z coordinate of this problem. Right. As a consequence of this, this medium in some sense develops a profile as far as this pulse is concerned, which is kind of like this, like a bulge or whatever. This is what we have indicated in the plot here. Therefore, the central portion of the beam much like in the case of a positive lens, the central portion after a given time t propagates a lesser distance as compared to the central portion propagates a lesser distance as compared to the outer sections, and this beam then starts to focus inside, which is what is depicted in this picture here. We have a medium which otherwise is sort of homogeneous, it is just a block, rectangular block. There is no shaping of the interface. Nonetheless, the wavefront essentially becomes concave, and the rays which are perpendicular curves to the wavefront lead to a focusing like effect. But here there is no lens, it is the beam going through an isotropic block of medium and it starts to focus on itself. So, much like self phase modulation, this effect is called self focusing. But this effect typically was discovered by Kerr. So, this is called the Kerr effect. The spatial domain effect is called the Kerr effect. So, self focusing or Kerr effect is important. So, also we would sometimes hear in literature the term Kerr nonlinearity being used, right. So, Kerr therefore refers in nonlinear optics to chi3 effects. So, Kerr effect is chi3 effect. Okay, this is not the Kerr of the black hole physics fame, this is a different Kerr, I think. So, Kerr effect refers to this idea. Now, these kind of effects where in some sense this medium develops a refractive index gradient, okay. I would actually say a transverse refractive index gradient. So, this is a form of lensing in a medium that is going on, right. So, this is a lensing effect. The same principle is actually used to make very compact lenses called graded index or grin lenses. Grin is, these grin lenses are linear optic devices, that is not nonlinearity. One plays around with the material properties in order to do this. Graded index or grin rod lenses are used in high quality laser diodes to correct for the ellipticity in the beam profile and produce nice beams. So, this is an example of a gradient in the refractive index or a graded index medium, but all happening due to the mere propagation of the beam itself in the medium, no other special engineering or technology required. This sort of gradient in the refractive index or graded index effect is also seen in another natural setting, actually in day-to-day observation. So, this is summer here in India, and especially in a hot city like Chennai, this should be it should be possible to observe this. If you are somehow unavoidably having to go out in the sun during midday, then look for a heated tar or asphalt road on which you can find this sort of a thing happening, right. That is the air that is close to the surface of a road. This is a desert. So, this is a denizen of the desert over there. Now, owing to the fact that the surface here is hotter than the air above, which is cooler, refractive index is a function of temperature too, right. So, hotter air means less denser medium. So, therefore, you essentially have a gradient in the refractive index as a function of, say, height z. So, if I plot refractive index, it increases like this, all right. So, as a consequence, what happens is that in this case, as a function of vertical height, the optical density of the medium assumes this sort of a form, but let me complete this picture for you. It starts to behave like a concave lens. What does a concave lens do? It defocuses the rays going through it, right. That's the conventional notion which we have been taught. A convex lens would defocus a beam. So, now when light rays come from a tree which is over here, the lens has this sort of defocusing effect. It is more complex physics than this. I am oversimplifying this a bit, but the point being that the essential idea is captured, that there is a refractive index gradient or a gradient in the refractive index, however so small, which is present, which bends the ray of light. As a consequence, the observer observing it from here maps this down to a virtual image where a palm tree which is present here appears inverted, and hence as though it is a consequence of reflection from a pool of water here. So, for a traveler in the desert where water sources are scarce and also could be a matter of survival, at least if not in modern times, in earlier times. This essentially gave the illusion of a pool of water, which when approached turns out to be an illusion. Okay, so this is of course the formation of a mirage. This is also a consequence of gradients in refractive index. This is an important effect, and this is actually exploited to produce this, meaning the Kerr effect, actually stable femtosecond pulses. We may have an opportunity to learn a little bit about that in the remaining parts of the course. Okay. So, with that I will make this little point that Kerr lensing leads to basically two types of sort of self-focusing effects. Since n, I should say not exactly but nearly equal to n naught plus n2 I, n naught is always greater than 0, it is the refractive index, it is defined by the speed of light in vacuum. If we denote the speed of light in vacuum by c, the speed of light, I mean this ratio of the speeds of light in vacuum versus a medium is the refractive index, right. Therefore, n0 actually, this is our n0, this is always greater than 0, no medium flips the direction of light. So, n naught cannot be negative as it turns out, but n2 can either be positive or n2 can be negative. If the self-focusing effect happens to be when n naught is greater than 0, self-defocusing happens when self-focusing happens when n2 is greater than 0, not n naught. Self-defocusing occurs when n2 is less than 0, and while normally usual media that are around us, say glass, it is a question of frequency, but very commonly glass or popular media with very relatively high Kerr nonlinearity or chi3 coefficients, such as the solution of carbon disulfide, which is very popular. These exhibit self-focusing in the visible and near infrared regions. Examples of self-defocusing would be scenarios where we sort of somehow generate plasmas or beam propagating in a plasma, say a laser generated plasma, or in laser plasmas, one can encounter scenarios where self-defocusing occurs. Okay. So, this is also an analogy in one sense of space sort of getting curved by the presence of something. Okay, this for a physics student may be an interesting analogy to consider, right. I mean such as what happens in gravitational physics. So, with that we have examined the effects of the intensity dependent refractive index both in the time frequency domain as well as in the spatial domain. With that, let us pause here for today and